back here to talk about a topic that I started studying, I think, 10 years ago, and strangely haven't applied all that much in my own research, although I actually spent considerable time thinking about how to do these kinds of models. As you can tell from the schedule, we'll be covering quite a bit of ground. I'll start with a very brief discussion of why we even need special models, why we can't just use regression analysis. Then I will talk probably a bit more than I originally intended about the hierarchical linear model, because when I sort of look at the various topics that are listed for PhD students, I think a lot of people will actually be using those models rather than the ones specifically for categorical data. We will get to those as well, but we'll probably switch these and shift the ordinal models to tomorrow morning. If anything is unclear in what I have to say, please interrupt. It sort of is a cumulative setup, so really the early building blocks are important to understand the data, bits and pieces. I've also tried to keep this a little bit less technical than I sometimes teach this. So we're not going to get awfully deep into things like estimation theory. Except I will have to do a little bit of that when we get to the categorical dependent variables, because there the estimation actually is not very trivial, and there are different options out there that people use, some of which are absolutely horrendous and should never be used, and some of which are actually quite good. And so I'm going to explain a little bit why. So we can go off for the wrong approach and get estimates that are terribly off and biased. So let's start with this topic, why multi-level analysis. Let me just start by saying what multi-level data structures are. In general, they're characterized by the presence of multiple units of analysis, at least somewhat of a hierarchical relationship that doesn't have to be complete hierarchy, but at least you should be able to say that some units are nested inside other units or combinations of other units. And importantly, the outcome variable should display variation across all of the levels. So when we think about an example, say you're studying democratic preferences, as I saw one of you, at least one of you is studying, then what you would like to look at is a situation where these democratic preferences vary across individuals, and they also vary across contexts, say countries. What we typically do, and this is the first bit of jargon I'll introduce, is instead of referring to units, we talk about levels. So I will be talking a lot about level 1 and level 2. These can have different meanings, as we will see in a moment. But the idea is that level 1 is nested inside of level 2. So think about one possibility. Level 1 is a citizen, level 2 is a country in which that citizen resides. Now, when we talk about these data structures, multi-level data structures, there actually are 3 different structures that people talk about in the literature. There are the hierarchical data structures, fully hierarchical data structures, then there are cross-classified data structures, and multiple membership data structures. I'm only going to talk the remainder of the course about hierarchical data structures. There are some special issues that come about with these other kinds of data structures. Let me just briefly explain what they are. In a simple hierarchy, it's pretty straightforward. So we have level 1 units, so say citizens, residing in level 2 units, say countries, and there is basically one level 2 unit for every level 1 unit, or putting it differently, every level 1 unit can belong only to one level 2 unit. That's sort of the simplest possible structure you can think of. It is actually not an uncommon structure. I think a lot of electoral data that we analyze are actually of this type. Now, what happens when we move to these other structures, cross-classifications and multiple membership structures, is that it gets a little bit more complicated in that there are at least multiple level 2 units, at least 2 of them, but possibly more. Now, with the cross-classification, what we have is actually level 2 units of different types. So, the example of countries doesn't really work there very well, but imagine that your level 2 units are, say, this is the classical example from education and research, neighborhoods and schools. So you can belong to a particular neighborhood, you can belong also, you can be attending a particular school, and it's not necessarily clear how these schools and neighborhoods should be rank ordered in terms of a hierarchy, so we usually put them on the same level, and that's then becoming a cross-classification. So you can almost think of that as a contingency table here, neighborhoods times schools, and then you have individuals living in the different cells of that table. With the multiple membership structures, we also have this feature that the level 1 unit belongs to multiple level 2 units, but these are all of the same type. So to carry forth this example with schools, it could be that we have a pupil, the level 1 unit, who switches schools in the middle of the year. So then you could say, well, there are 2 schools to which this individual belongs, and that's what we mean by multiple membership. And then in the analysis, what then happens is you want to weight things. You want to say, well, what portion of the year was this pupil attending the first school, what portion of the year was he or she attending the second school, and that then is incorporated into the analysis. I'm not going to talk about these two for a variety of reasons, the most important of which is that we just don't have time to do it. The second of which is that I don't really see many applications of these things in political science. What you see in electoral research, for example, is practically always these simple hierarchies that we use. Now, what are then in these hierarchical data structures some of the common levels? Well, I already mentioned individuals, and then we have cross-sectional data that is typically our level 1 unit of analysis in electoral research. But if we have panel data, we can also take the different measures that we've taken over time and make those the level 1 unit. So we could say, well, we have a panel, say, of 3 waves where we repeatedly have measured people's attitude towards democracy. And we could say, well, we have these 3 measures, these 3 time points. They are our first level, and they are then nested inside individuals. And that would then be the level 2 unit for that kind of data. And then, of course, you could add additional units on top of that, like countries and things like that. More commonly, when we have cross-sectional data, The level 2 units are geographic units, constituencies, regions, countries, things of that nature. They could be temporal units in repeated cross sections. That's a little bit different from a panel where you have basically not the same individuals at multiple times, but you still have a time dimension. Or it could also be social units. If you, for example, interested in networks, you can say, well, the individual resides in a particular network. And with these networks, actually, that's one example where cross-classified structures would probably be useful because the individual can belong to multiple networks of different types at the same time.
Oh, sorry, there's one.
Yep.
I do have a question
Yeah.
related to the, when we have measures at level 1
Yeah.
in the panel data, how many waves do we need in order to have a network multi-level data? Because I know that the level number of units in level 1 is important. So if we have only 3 ways, can we use it?
Yeah, it depends a little bit on what you want to do. The general rule of thumb actually with multi-level analysis is that the number of level 1 units is not nearly as important as the number of level 2 units. So with panel data, that problem usually is that, so you have 3 time points. That's not as bad as having, say, only 3 contextual units, 3 individuals. But there are limits, of course, to what you can do, because one of the things that people fit, for example, with these panel data are things known as growth curves. And that's basically sort of you estimate for a single individual a trajectory of change over time. And usually what you do, or at least one way to do this, is to make time a predictor, and then you add typically some polynomial terms for time, so time squared, time cubed, to basically capture the trajectory of change. But of course, how many polynomials you can add depends on how many time points. So with 3 time points, you're pretty much stuck with a quadratic function at best. So that is then the limitation. But other than that, it's not that problematic if you have relatively few time points. It's just basically what and I think Chris will also talk about, is if you have that few time points, the time dimension just is not something that you can exploit so much. There is just limits to what you can do with that. So. But I mean,
like only using multi-level modeling for panel data and transformation, is it enough to have 3 vectors?
Yeah, I've seen people do it 3 times less. Other questions? So why do we like to have these data? Well, the most important, of course, is that we can exploit different sources of variation. I mean, you probably, some of you were using these kinds of data, really sort of interested in both individual and, say, cross-national variation, or variation over time and variation within individuals. The other point, and I borrowed this term from a paper by Bruce Weston, although I'm not a big fan of the term, is that it allows us to introduce causal heterogeneity. And I've put causal here in quotation marks because there's really nothing inherent about multi-level models that makes them causal models. Not any more than a regression model is a causal model. That isn't a causal model either. You have to be, in order to give a causal interpretation to these models, you have to be very careful that you control for spurious relationships. But the idea of causal heterogeneity is a powerful one. It's the idea that relationships may not play out the same across contexts. And there that we basically could engage in what some people call the condition-seeking approach to science, rather than sort of saying, is there a relationship, which is what we frequently do, go more into the question, well, under what circumstances is there a relationship, and under what circumstances is the relationship perhaps positive or negative. And then finally, although that's usually not a problem we have in electoral research, it's a way to increase the sample size. Now, here are some things that limit what we will do. I will only talk about hierarchical data structures, as I already said. I will focus on two-level structures, although it's generalized all fairly easily to higher-level structures. It's got the problems of interpretation and data requirements just multiply. And I also only will deal with cross-sectional data in the course. If you have data that are not cross-sectional and you need some advice, I'm happy to talk to you either these 2 days or send me an email. Their issues are not fundamentally different, but there's some things you have to pay attention to. Now, why do we not just analyze this kind of data with regression model? Let me just say a little bit about what a regression would entail, and that also allows me to introduce some more notation. So we have an outcome variable, y, and I'm subscripting this now in 2 subscripts. In a normal regression model, you only have one, which is a subscript for the single unit of analysis that you have, say, the individual. But now we have added level 2 units, say countries or other contexts, and we need to indicate those as well, and I do that with a subscript j. So I always refers to the level 1 unit, j to the level 2 unit, and the combination of subscripts I, j means that we have an outcome y that indeed varies across level 1 and level 2 units, or at least could. Empirical matter if it does. And then we can add predictors to this model, and the nice thing is we can actually add predictors at both levels. So we can introduce a predictor x, which is also for, say, individual I in country j. That's the level 1 predictor, but we could then also add a country characteristic as in this predictor zj. And that's the level 2 predictor. And those level 2 predictors, in general, they can take on 2 different forms. They can be derived variables, that is, they can be summaries of the level 1 predictors or even the level 1 outcome. So what I've seen used, for example, is if you want to have sort of control for the average of some outcome, you calculate the average in a particular context and use that as a level 2 predictor. But sometimes these level 2 predictors cannot be reduced to level 1 attributes. We call them in that case integral variables, and that would be something like a country's type of government, type of coalition government, say, at a particular point in time. Now, what would happen if we just run a regression analysis on this? Which you could do. You could type regressance data, specify your dependent variable, your level 2 predictor and your level 1 predictor, and then run the thing. And that would be sort of the equivalent of a pooled analysis in panel data. And there are 2 problems that you might run into with that. One is bias, and the other is incorrect standard errors. And the bias would arise if there is causal heterogeneity that you actually are missing. Because if there is causal heterogeneity, then you should specify that, for example, through an interaction. You're leaving that interaction out of the model, you have specification error. If you also forget the level 2 predictor, then that may also introduce in its own right bias. And so, in both cases, we have omitted variance bias. And this is just an illustration of how that may play out. I artificially created 3 sets of data here, 3 groups, group 1 here, group 2 here, group 3 here, where I took advantage of the fact that, that I wanted their slopes to vary as well as their intercepts. So I have a positive relation here, I have a slightly negative relationship here, and I have a flat relationship here. And the black lines that I've drawn here are the group regressions. You can think of as the within group regressions. So this is the regression line in group 1, the regression line in group 2, the regression line in group 3. I've also drawn in here what you can think of as a between regression line, which is basically take the mean of y in each group and regress it on the mean of x in each group. And then you get this red line. And then the pooled line, which is basically treating all of the data as if it was really just coming from one single level, is this green line. This is the pooled regression line. And this pooled regression line is a sort of compromise between this within and this between regression. It's a weighted compromise, so it weights the between and within by their reliabilities. But what you can see easily here is that that green regression line really doesn't do justice to the relationship in any particular context. In fact, the green regression line says it's a positive relationship between x and y, when actually it's only positive in one of the contexts, and the other contexts it is not. So this is a kind of situation that you have to be very wary of. Now it's of course fairly easy to detect it in this case. You would just run a scatter plot and you will immediately see what the problem is. But sometimes it's more hidden, and then you worry a little bit. Now that's the problem of bias. And then in addition, we have the problem of the standard errors. And the problem here is that the ordinary least squares, standard errors that you get with a regression probably are going to be too optimistic. They're too small. And the reason here is that these OLS standard errors are computed under the assumption that the observations are all independent from one another. That they basically are generated, if you will, through simple random sampling, which is actually, even on a very superficial level, often a very strange assumption to make with survey data when practically all surveys that I'm aware of use a multi-stage cluster sampling, which already violates this independence. The only one that I can think of that insists on not doing that for very odd reasons, but I have not been able to persuade them otherwise yet, is the Swiss election studies, which insist on using simple random sampling for reasons unbeknownst to me. But usually, we have some dependence between observations already by virtue of the sampling design, but when you then start thinking about context, then we really have some dependencies. And we call that the problem of clustering. And the problem here is that observations from within the same context are not independent. Why? Because there are probably some unobserved characteristics of that context that give some similarity to these units. Shared culture, shared history, things that are not always easy to measure, but that make, for example, two people from Turkey more similar than a person from Turkey and Germany. Now, the degree of clustering is measured through something known as interclass correlation, which is a correlational measure of how homogeneous the observations from a context are. That thing runs in theory from -1 to +1, but I honestly have to say I have never found a -1 in anything I've done. So for all intents and purposes, it runs from 0 to 1. 0 means essentially the observations are independent. 1 means if you have one German, you've seen them all in terms of your output variable. Effectively, you could sample 1,000 Germans, but 999 of them will add absolutely no additional information about what you're measuring. Now, in nearly all social science applications, as I already said, this ICC is positive. And this positivity is important because recall in a regression analysis of time series data, you might have positive autocorrelation. Under positive autocorrelation, all less standard errors are underestimated. It's the same with multi-level data structures and a positive ICC. Another way to think about it is that the effective sample size is actually less than you think. That's the point I just made. You think you have 1,000 Germans in your sample, but you really only have one, because 999 have no information. Is this a big problem? Well, actually it is, and it actually is a problem that gets worse under certain circumstances. I mean, one argument that I sometimes hear is, well, but in a typical survey study, this interclass correlation is only about 0.05, so who cares? Close enough to 0. But what is forgotten is that the impact of this interclass correlation on the standard errors depends not just on the size of the interclass correlation, but also on the number of observations in each context. And we'll be calling that the cluster size. How many observations in each context? And now I have basically, for a simple regression model, indicated here what happens to the standard errors for different levels of interclass correlation and different cluster sizes. So you sort of think about this is the worst case scenario. All the Germans are the same. This is, well, only 5% they have in common, say. And these are, say, different sample sizes. So this is, you have 2 Germans in your sample, here are 5, here are 10, here are 50, here are 100, here are 1,000. Lots of electoral studies, of course, are more on this end than on this end. And so what happens? Well, in a simple regression model, if you look at the ratio of the true over the standard errors you get from OLS, you see that even with this 0.05 that people say you shouldn't worry about, if you have a large enough set of observations in a country, say, your true standard error may almost be twice as high as what OLS tells you. Now that has huge implications for confidence intervals, for hypothesis tests, all of those things. And that is just one example. Here I've also made a simplifying assumption that actually the degree of clustering on the dependent variable in the predictor is identical. That doesn't necessarily have to be the case. So you see this problem actually is often not as small as we might think just simply looking at the interclass correlation. But what could we do? Well, there are a couple of ways to approach this data. I'm not complete here. One is to do fixed effects. Just as you could do with panel data, you could just throw in fixed effects. Basically, in this case, it would mean level 2 dummy variables, possibly interacting with the level 1 predictors. It's a quite inefficient way of going, and what is actually worse, I think, from a research perspective, is that once you have introduced these dummies, you basically have no more degrees of freedom to add substantive level 2 predictors. So if you want to come up with a substantive story of why things vary across contexts, you're on a and it's not entirely clear whether you can generalize this to nonlinear models such as longitudinal probing models. This gets you quickly into the problem that statisticians refer to as the incidental parameter. Second approach, and this is one that I think is abused because data makes it so easy to do this. Treat clustering as a statistical nuisance. Just say, well, so there is this dependence among observations. Who cares? I just want to take care of it in the estimation of the standard errors, and for the rest, I don't want to think about it. And you can do that. Stata makes it extremely easy to do it by computing so-called clustered standard errors. But that only addresses the problem of the standard errors, not the problem of the bias. Secondly, it basically takes care of the clustering in the dependent variable. It's not so clear what it does with the clustering in the predictors. It doesn't easily generalize to higher level models, at least not the way Stata implements it, so you can only specify one clustering variable. So the clustering variable would be your country or your primary sampling unit, but if you want to control for other varieties of dependence, you can't do it. And again, it's not so easy, not easily seen how it generalizes to these nonlinear models. So we have then as a solution, a general purpose solution, multi-level analysis. It works well when the model is correctly specified and when other conditions to be discussed later are satisfied. At the very end of this part of the course, the next part of the course, I'm going to actually talk about some things you have to be wary about when you run multi-level models. So, are there any questions about this? Then, let's